Doesn't mean it's your last opportunity to ask questions or everything like that. I did circulate the email yesterday asking you guys to think about the module and tell me what you remember, what was unclear, and I'll try to follow up with you fairly quickly. What I wanted to do today is very much a combination. So we'll go back to the outline of the module and I'll summarize it briefly, but to keep it interesting, I bring a lot more example for each categories. And there are a few things, of course, in trying to cover so many different topics. There are a few concepts that I don't think I highlighted, so I'm going to try to rectify that so that you can think of it as a wrap-up. And then I have some discussion I want to have with you about more advanced manufacturing. We'll talk a little bit about laser sintering of metals. I have an example of it here. So let's get started with casting and solidification. And because I've talked more about metals, I thought I'd bring a plastic to begin. This is, what, by the way, people learn different ways, I'm sure, you know, engineers, but getting a product, getting pieces, or getting a prototype really makes you think. You know, we could go all day long going over what injection molding is, but when you look at just this piece of equipment that they sell for $30, it has a lot of process engineering into it. For one thing, if you remember the video I showed about die casting, they had inserts coming in two different ways. So this part was built that way. You had the mold, but you also had pins coming in to make for the holes in the connection. So this built as a single piece by injection molding all the way to the black here. And the aspect that's interesting to us, it did fail. It failed at the point where you essentially tighten it against the silcock outside the house. So I just blew up the detail here, and without calling the manufacturer, I think we have to be a little impressed, because the only way this system works is if they injection mold the nut and the body at the same time, because after the fact you can't put one into the other. So they had essentially the mold built to include the nut, which is this component, against the end of that pipe that had a flange on it. So I'll circulate it, but you'll see that where it cracked is right here. We can't really blame, we can't really blame that it was an improper orientation, because essentially for this part, the green part, the resin was flowing up and turning around, and this just ending here. What probably we can anticipate is there wasn't much orientation. There wasn't much skin effect created at that location. But my main concern with this is, and when you get to see it, you'll be able to make your own judgment of this. But I don't believe that this component was thick enough to prevent it from bending a little bit. So if you start bending this flange, you generate a lot of tensile stresses in the area that you already have a notch. Now, we're not going to refute the fact that I did use it for a year. I didn't abuse it, but I did use it for a full year.
These things last longer than that, though?
Yeah, I mean, they don't have an expiration date. So how we could do this specific molding to avoid it, I think thickening the flanges is one parameter to essentially avoid the bending here. And then what you'll see me say a few times today, I try to get a focus for each lecture, is why did they not put a good, nice radius there to prevent high stress concentration? So what happens is locally, you can take it that the stress has to transfer from this wall all the way to the support here against the nut. And if it's a sharp corner like the one that we have there, you expect the local stress to be between 3 and 10 times higher than the average stress. So you can make it 3 if you have a radius, or you can make it 10 if it's really, really sharp. So it seems obvious that you would want to have some radius to the extent that you make this thick enough so the fact that you're not touching for the first little portion doesn't make a big effect. So you have to make the 2 changes. If you just add this corner and then you make the ID of the knot a little bigger, then you're increasing your bending moment on that flange. So it's part of, when you think of it, is that there are a lot of corners into this, but there's only one high load point, and they design it just the same as everything else. If nothing else, they made it a little thinner here. Now, and I think that you had plenty of room to make that distance bigger. So there's just no excuse. But if you wanted to go to the extra step, because assume that somebody, and I don't know that they say that you can't do that, but if I decide to use this in my home, and it falls this way, it's not just creating a big puddle on the inside of the house, it's creating flooding. So there's a good reason why you would want the input that's always under pressure to be a very resistant design. So there's nothing to say that you would not want to have a metal fitting to tread into this housing, just to make sure that regardless of the detail of the load or how long it's used, that it's not going to fail at that critical connection location. I've seen that a lot where if you have a big amount of metal, of plastic, like the housing, it's okay that you can come and tread in the fitting, and it's going to just really work in shear. The problem in this case here is the risk for bending and tension from the stress riser. So it's unfortunately typical. I have another example of that later. It happened recently. I had a project that was using an aluminum casting, and it's a yoke system. So what happens is over here, you tread in a rod, and that goes for a hoisting mechanism up on top. And then here you had a pulley to carry the load through a number of cables. So we're just looking at essentially that U shape that was cast aluminum. And they had the very same problem where this corner here was sharp. Now, this is, to me, even worse, because there's just absolutely no reason why it would be a disadvantage to just round the mold in those corners to create yourself a good radius. Now, what happened, because they did not have that radius, is there's a little eccentricity here where you're loading, the distance is smaller than the distance here. So just by pulling on this, each eyelet or each tab is going to try to straighten. So it's going to bend this way, just by having the contact with the pin here as opposed to the support over there. This just try to rotate. So you have the contact going on over here. You're opening it, even though you're just loading it in tension. Creates very, very high stress at that radius, and it will not be a problem if we had steel there, a wrought steel that was machined. It will just stretch, but because it's cast, it has the porosity. It's got all the structure from solidification. It just snap literally all the way across here. Tension load, the stress riser. There was potentially a little bit of an impact. What's I think is the most troublesome, we just found out last week, they still make it the same way. So we're going to need to do something about that because there's just no reason not to put a nice little radius there to reduce, cut by half essentially local stresses. And I don't know how familiar you are with stress analysis, but anyway, let's say that here I think of stress line in the material just holding the load from the pin. So I have the load from the pin here, it's transferred there, it's localized here, and it's spreading. Now, ultimately, it's going here. So, of course, when it gets to this corner, the tensile field is going to be very, very, very turning a sharp corner, and that's kind of an exemplification of the stress riser. Now, when you have the radius here, the material knows already that it's going to turn, and it's adjusting to it, so the profile are a lot more regular. There's more anticipation that the stress field is going to change, so it distributes more nicely. So factor of 3 between one and the other, approximately. So if you're thinking of a factor of safety of 2 to start with, and you didn't account for this, it's a difference between a failure and no failure. It's very unfortunate, yet it happens a lot more often than you think. This particular issue of stress risers in fittings, any equipment subject to vibration, compressor for natural gas equipment, I've seen it too many times. It's just so unfortunate because let's say now, let's take the next step where we have a very nice forging of steel, or we have, what else could we have? Just a very nice machining part of steel. And we have this condition, but it's not a constant load. The load is varying here. So instead of the steel deforming once and holding for a very, an infinite life, it starts weakening because each time it's forced to expand and compress locally, and that's what we call the fatigue. These corners are, sharp corners are important if you have low ductility, and even if it's just a single load, or any material if you're going to have these cyclic loads, if you know that it's going to be vibration. Anything connecting to an engine is going to need to have a very careful analysis of the radius that comes out of it if you have some cantilever action that causes side loads on the connection. All right. In terms of casting, there's something that I think should be done more often. So that's always interesting to bring that up in a class. I've talked a little bit last time about blowout preventers for closing wells when we were talking about drilling. So here you have that drill pipe, the high-strength steel pipe we were talking about. It's going down, and we said that we need an annular space to have the flow of the mud coming back up. So this equipment fits the purpose of fitting between the pipe and the bigger hole. It's a little more complex, but for us right now, let's just keep it that way. So the bigger hole is only this big. It can be this big, but then you need more equipment. So the way, the simple design, and there's a lot of variations of it, it's these two C shapes, they come together and engage with high closing forces. To get you an idea, you're looking at 10,000 psi of difference in pressure one side to the other. So it's if you use the solid aluminum, it will deform. So this is all steel, and it's supported from other components. Now, steel is not going to make you a fluid-tight seal. So there is a very high-quality elastomer between the two plates. It's a sandwich construction, a little bit like an O-ring. And what you do is, by the time it's closed, it's steel for the first 6 millimeter, it's steel for the lower 6 millimeter, and then the elastomer is confined in that space. And one properties of elastomer is they don't compress, really. So as you keep energizing this, it can't go anywhere, so you build very, very high pressure into the elastomer, and that's how you get the seal. So the purpose of the metal is just to hold everything in place, and then you make the seal. you can have a lot of variation of this where for some reason you wouldn't have the metal close enough to each other, and then the elastomer is just going to extrude out. That happens. So there's a lot of optimization in making these. But by the time you have it designed, what's really interesting about it is you can take all these metal inserts. So there's the two plates, and then there's these pins coming in to attach it to the back. You essentially put all of these in the mold, and then you inject the elastomer. You'll see the injection ports on the back here. And there you go. You know, you have a part. You just have to let it cool a little bit, and it's over, all in one step. No machining, no nothing. It's a little heavy, but there's nothing wrong with having a look. So you have situation if you wanted a reinforcement. It's done a lot with composites. So say you have a large boat, a sailing boat. They'll put a lot of metal inserts on critical component that needs to be very stiff, and embed them in the composite. That's an example of doing it. But for injection molding, I think it could be done more. You know, there's no reason why you wouldn't put more parts in there and position them exactly where you want them. All right, let's go. So over here, we haven't really talked a whole lot about the segregation. I think we dealt with this at the beginning. The heat transfer and the processes, if you remember, there was this not resin transfer, but lost wax process where you essentially make your jewelry and then you make a mold out of it. You fuse out the wax, and you can make any complex part you like. You know, it's one of the limit cases, but I think that in general you have the metal mold. That was the die casting, very, very fast process because you have a high cooling rate, so you get good properties. So there was just a lot of variation. Is there any casting you guys would like to build? You know, any question on casting? Because we can move to deformation processing after. But you make very complex shapes. Looking at this here, it's got a lot of features that it would be, you know, you wouldn't, if you were to machine it, you could probably get by with a design that has less features, but there's no problem if you're going to cast it anyway. There's no problem making it a more complex shape. So the lost wax, essentially, you can build up the shape that you're looking for. And then you dip that shape in a slurry that's the mold material, and it's building a shell around it. Now you can put it upside down, you raise the temperature, the waxes melt, it gets out of your new mold. So now you have a mold that you're going to use once. We also call that investment casting because your mold really serves one part, because after that you have to break it to get your parts out. Now, so I think we can all agree that there are more components that are subject to all this high temperature rolling and deformation processes, because it does get rid of the casting microstructure. And we went through some metallurgy of this, talking about, you know, dislocation when you're hot and you have these grains. And, you know, I went a little bit deep there. But one aspect perhaps that I didn't emphasize enough is if you're thinking of stainless steel is the best example. If you want to use stainless steel like this one here, you would like the stainless to have, you know, relatively high strength. Typically, stainless steels are relatively soft. So one way to do that in terms of the deformation processing is this the cold rolling or hardening by deformation. So when we refer back to our stress strain curve, I think what we discussed at high temperature is we're going to have our stress or deformation, and it essentially is going to go to a certain transient regime, and then eventually it's a constant stress. That's our forming condition. It's perfect for rolling because you have a competition. You keep recrystallizing grain. You have a lot of recovery of dislocation, so you get into this steady state. When you do it at cold temperature, and if we do the tensile tests, you know, it's going to look like this. Now, we discussed together that in reality, the material is going to deform this way. So to the extent that you avoid the tension mode of failure, you're able to continue raising your flow stress in the material, the strength of it, by deformation. So and typically for stainless steel or even aluminum, they'll have an H dissociation. So say I'm just coming up with one here. I have a 3000 series aluminum alloy that's got a certain hardening. Maybe it's got a number to it. So this means that it's being cold formed. And it's very useful, just even in terms of machining. We have some stainless steel parts that you get the wrought product in hardened condition, but if you're going to try to machine it, it's a lot easier. Otherwise, let's say I want to change the entrance to this, create a little chamfer and make a connection. If it's really soft, I can bend the whole part by the time I'm done, just in handling and trying to do the work. So I want this part to be hardened at the beginning, and then maybe for the application, I was talking about medical devices, probes that needs to be flexible. So that's an example of a tube that is very flexible. So it was cold work to make some details. Let's say I want to work any details, and then you anneal it, either to create more and more deformation. Like, let's say I shape it this way, then I start feeling like, oh, it's getting a little harder. I could increase my ability to deform it by annealing it again. There's no limit to this. Because at some point, let's say it's starting to be a little harder here, and I start deforming it. Oh, I got a kink. That's not ideal if you're trying to form tubes. So there's always going to be a competition when you're trying to do your forming on how much hardening you're getting to get a stability. So when we were talking about forming aluminum cans, it's the same process. If you get in a situation where the aluminum now is so hard that you can't easily deform anymore, then you want to anneal it again. So you lower your flow stress, you go back here and start over again. So there's a lot of opportunity to think about with respect to the original condition that you'll start your material with. So when I was talking about here, we were talking essentially about hot rolled or and cold rolled. So one thing I remember mentioning that was, relatively simple is over here you get more precision in your measurements. But again, what I was not emphasizing enough is you become a pre-hardened condition, which is an advantage if you're trying to build a power line or anything that is very demanding. It would be a very high disadvantage if you're trying to do additional forming of the component. All right, heat treatment. In heat treatment, we talked a lot about quenching, and you've seen it with the large chains. And what I explain is the main difference between aluminum and steel for what happens after the fact. In one case, you make it harder. That's the aluminum by aging. And with the steel, you temper it, you soften it by transformation. So that was relatively clear, I think. We didn't emphasize enough why we would do annealing. Perhaps you can see it a little bit here. So as part of forming operation, you can generate a condition where it's very high strength but low ductility, so you anneal it to get back that ductility. That's one application of it. The main difference with annealing is you don't have a fast cooling rate. That's pretty much the definition of it. Stress relief, I brought it up when we were talking about our gearbox systems for radio telescope or other very precision structure. One thing that I may not emphasize, there's actually a temperature. So for steel, typically, this happens below approximately 1200 degrees Fahrenheit. If we refer to the phase diagram for steel, it means it happens well below where we transform into that high temperature phase. So there is no real phase transformation associated with the stress relief. Your properties don't change very much. So it's a big advantage. You essentially get to reduce any form of residual bending loads from forming into the material without having to change the microstructure and the mechanical properties. So let's, yes?
Does the annealing change the density of the dislocation?
Typically, yes. So when you do annealing for steel, you revert back to the austenite, the high temperature phase. You get a lot of opportunity for diffusion, and you reform the low temperature phase during your cooling. So it's an entirely different material. It has a very low dislocation density. If all you want to do is reduce the amount of dislocation, that does happen in the stress relief as well, a little bit. Not as much, but it happens. So the idea with the annealing is really, it's a general term, so you can have recrystallization during your annealing if it was really cold roll. Yes.
So for stress relief, that's like a kinetic argument? Like higher diffusion?
Okay, so because the stress relief, because it's a lower temperature, what happens is you're reducing a lot the yield stress of the material, so it will deform by itself. Is probably the best way I can explain it. So you have so much thermal energy that you can have the dislocation remove the stresses by movement. It's really soft at that temperature, but it doesn't require any change in the grain structure or the microstructure. That's a very good question. Okay, so in fusion welding, there's an example that came up with respect to the you guys competition with very miniature sports car. Jimmy, he's not here today, but he did some research because I said something earlier in the class about, let's do it here, 4130 steel. So that's a type of steel that gets quench and tempered. The designation here just means that we have 0.3% carbon by weight. This number tells you that you have a little bit of chrome and you'll have a little bit of molybdenum. And typically, it's an AISI specification. I said that this material, normally you don't want to weld it. So, of course, there's an exception to it. So Jimmy came up with these tubes for little race cars that are relatively thin wall, kind of the opposite of what we looked at for the greenhouse, where the entire interior is very small. So if I have two of them that I'm trying to weld. Let's say I'm making a joint here. Yeah, let's just do it at an angle. So we have these two components that we're trying to join together. And this is going to be the interface between them. I typically won't need a big preparation, so I can just put a weld on top here and assume it's going to be all right. If you go, when we were talking about sport equipment, bikes, and all this, we said actually a lot of times the weld is going to be a little bigger because you don't want to heat the base material too much. It's very thin, otherwise you'll get a burn through. So one aspect that ties a little bit of everything together here is you'll see that with this geometry, if I'm adding as much, if not more metal than the thickness of the member that I already have, when it's the time for cooling, it's not the heat affected zone that's just next to the weld here. So say this becomes my fusion zone, so I have my heat affected zone here. The heat affected zone is not going to cool as fast because there's no room for the heat to go. It's a very thin wall. So even before the weld gets deposited, ahead of the traveling welding electrode, there's going to be some heat coming up here. And after the fact, there's not much room for the heat to go, so your cooling rate is relatively slow. So what they did for this race competition is instead of using the standard AISI definition, they became with the SAE definition of a 4130. And for that, there's manganese here too. They reduced the manganese content, they reduced the chrome content, which you're allowed to do, and they're able to weld this. So one thing that I know was a little difficult to follow, and I think it's going to be easier here, is if we're looking at what happens with respect to temperature and time. And say right up here we have our red steel, so that's the austenite. You have the austenite and you're trying to cool to the ambient temperature. If you're trying to do a quench, it means you're trying to avoid the normal transformation from taking place. So what you have in your note, and that may be a little difficult to follow, is these lines showing the conditions that will transform you into an equilibrium phase. So that's the equilibrium transformation. Starts. And that's all because of our nucleation process. So there's a certain temperature decrease where there's a good combination of driving force from the thermodynamic and there's still enough energy to make it happen. So it will start transforming then. So essentially a typical 4130, the curve is going to almost cross the 0 time. So as far as beginning of transformation. So if I'm cooling a regular 4130 steel, I'm going to start transforming into my equilibrium. No, it's the opposite. I'm sorry. So that would be our AISI designation, and that becomes the SAE. The SAE has less of these alloying element that delays the transformation. So if normally, if you take just carbon steel, if we forget about adding all of this, it's difficult to quench a carbon steel all the way through the core. And therefore, what we do is we add these alloying element that pushes the equilibrium transformation. Our goal, if we're going to do a quench of steel, is to avoid these equilibrium transformations. So by essentially removing some of the alloying element with the SAE grade, you're able to avoid forming the martensite during welding. And it's a combination of two factors. The first one is your cooling rate is not as fast, and then you don't have as much alloying elements, so your curve is actually closer to the equilibrium. It's hard to go all the way down in temperature without hitting this beginning of a transformation. So that's a continuous cooling diagram. Bless you. It's used a lot to compare different alloys for their ability to be quenched. So maybe one thing that it does bring up is we have to be very careful with when we're calling up for alloys, because if you have an ASTM or AISI or SAE, they'll have different specific requirements for alloying element that affects the ability to quench. One concept that is useful here is with respect to, especially with respect to welding, is the amount of carbon affects a lot whether you hit that curve or not. So the curve is going to shift with the amount of carbon as well, because that's what you need to diffuse to form the equilibrium phases. So you have essentially equations that will agglomerate the effect of carbon, chromium, molybdenum, manganese. So when you have, if you know exactly what type of steel you have, you can determine whether or not it can be welded without becoming brittle. And that's the concept of the carbon equivalent. So what they did with the carbon equivalent for the SAE is they reduced it, so it's a little bit more of a pure material, and the pure material starts forming the equilibrium phases more quickly. So everything essentially that's added to the steel, especially the chrome, is a barrier for the diffusion and the transformation into the pearlite, this lamellar structure that we've talked about. So that's really how, I guess, after a few time talking with Jimmy, we realized that we didn't understand why you can do it without the risk of having a low ductility.
What is the formula for carbon equivalent? There's some formula, mathematical formula?
Yeah, for the carbon equivalent, there are 2 or 3 formulas, depending if it's AWS or SAE. They all have their own slightly different ways. It's not a perfect system, but it really gives you a good starting point. So I've done that with respect to the carbon equivalent. When we were working, let's say, on an MBTA connection for the T that was built, they have no records, and they say, can we weld this beam to this beam? So just took a little sample out of each to do a chemical analysis, and then we were able to arrive to a procedure to do it. Just the chemistry. It's nice, because if you had to also analyze whether it was cold form, hot form, what kind of grains it had, it would require a lot more samples. So all we had to do is get some chips from drilling a hole. That's all you need to do the chemistry for that. Okay, we talked a little bit about tool steel. That is perhaps the one exception I said where we have our martensite in a hard condition used in service. So what I did is I brought a piece of a disc. So it looked like essentially a crusher. It's a piston going down into a cylinder. Was used to compact powder, I think. This was part of a powder metallurgy process. So what happened is, nominally, you put your force down in the piston, and here you compress the powder to make a part. The problem that they probably had is there was a little bit of powder inserted between the cylinder and this piston to create enough friction that there was also a force going up each time that they were lifting this to change the part. So what you'll see is that it cracked right here. This goes this way. So it cracked like this and merged into the center. You'll see the final fracture is a very, very small hole in the center. And there's a lot of crack propagation lines, so you can entertain yourself with this one. And you see the biggest facet, this one right here, is the first initiation. And everything else started to go out in all directions. So from a top view, what you see on that fracture is the first initiation here. It's a bigger facet. And then everything else is going like this a little bit. It's curved. And then in the end, they really emerged like this. So this is where it started. Exact same problem than what we talked about. Why not putting a nice radius here? It is an extra step in machining because you may need to use a different tool when you get to that part of the process. But that's how they could have easily avoided what happened in the friction condition. Now, the reason that they used the tool steel is this was very, very going to be prone to a lot of abrasion. They were crushing something very, very hard. So they needed this for the face. Whether they needed it for the entire section, that's another question. You could always take the lower part and braze it to the assembly above it and avoid this issue altogether. So I think that it does speak to an issue of using a very high strength material in tension. When we did a detailed failure analysis at a very, very fine scale in this zone here. So say I take this zone and I'm under the electron microscope we had to go approximately 20,000 times magnification. What you can see is these very, very fine lines for each time that the punch went through, the crack grew by a certain amount. And those are the fatigue striations. You don't always see them. It's very nice to see them, a little bit like when we were talking about looking at dimples on the fracture surface. You see dimple, you know it was an overload fracture. So you see those very fine striations, you know it was fatigue. Now, you can have fatigue that will not leave those lines behind. That's very common. So it was very difficult to find them in this situation. It was a little bit more of an academic exercise because the problem here just led itself to that it did fail in fatigue. Also, the very, very small size of the final fracture speaks to how little load there was applied in there. And I think it also says that it was a little bit of a bending load. If it was just really a straight pull in order to initiate at these different locations, you would have a bigger final fracture. But essentially, if you have more friction at one specific zone around the entire circumference, you start getting some particle buildup here, then this is where your bending moment starts, and that's why you only have one initiation as opposed to initiations all around. So there's a lot you can learn relatively quickly without having to do that microscopy study here. So the tool steel industry has very different objectives, of course, than a structural material. A lot of new parts are built with the powder metallurgy, especially in the automotive industry. And we haven't spent a whole lot of time. I think I mentioned it a couple times. But the idea with the powder metallurgy is you don't have the segregation. If we go back to our outline, like you have in casting, you do have porosity because you're coming with a bunch of little particles together. So I'll just describe it briefly, then I'll circulate this around. So you take the powder there are two main ways to make it. You can mix powders, and that's done very often now where let's say you want to make a tool steel, so you might as well bring some carbides with a matrix together. That's a very, very efficient way to do things. If you try to build an alloy, sometime you can get, we had some tungsten disc for X-ray sources. I remember you could get the pure tungsten or a tungsten rhenium 20%. So what they do is you put a certain amount of each powder if you want to make a 5% mix, because it's going to go to high temperature anyway, and it does get blended together if you cure it enough. So you essentially do a lot of times if you do the powder metallurgy, and to get rid of the porosity, you can either do a HIP process, so you hot isostatic pressing to remove the porosity. Now you have shrinkage when that happens, so there's a little bit of a limitation. Or you will forge it. So it may look a little interesting, but essentially, we know from forging, if you remember the schematic, I take a little cube and I try to squeeze it, and it starts to bulge on each side. It's very hard to forge a complex part from a block of metal. So the idea that I get approximately the shape I want, and then I get a little forging done at high temperature is fairly practical. So they will do it for gears, they will do it for specific application. You really want a good wear resistance. You want to very control your properties. The other place that more recently we've used a fair amount of powders, although it's limited in size. So this is additive manufacturing of stainless steel that essentially you lay a layer. It's built by layers. So you lay the powder on a bed. You come with a laser, infuse what you want, you add more powder, and you keep building it up. When you're done, you take every powder that was infused, and that makes the part. So I'll circulate it so you can see the type of details that you can generate at the same time. It is possible. So the way this one was built was from the below up. So you have the flange here at the bottom, and then you're going to your column, because you couldn't just go this way and all of a sudden become bigger. So you have holes here that go all the way from one end to the other. On the other side, you can see a column. So it's all the way drilled all the way through, very deep. What you'll see is there's a center column. Let's say I put it at this center column that you'll see. It has a hole in it, but the point is there's one strut that's holding that center column to one side. If you look on the other side, so you are able to build these features to hold the center here, but it has to be done gradually. So we had to build it up from each side at an angle and gradually add more material. Now, there's nothing about this. It's cool. You can make very complex shape. It's very controlled, the heating, so you can calculate the amount of distortion you can get. So you can essentially build it slightly differently and account for how it's going to bend in the first place. Now, there is a size limitation. As the suppliers we were talking to a few months ago, now they may be able to do bigger, but 1.5 to 2 inches is about how they can practically build. Not so much because of physical limitation, but a cost. Yeah, eventually it becomes expensive and you just want to combine. But it does allow you to have very intricate very intricate part. It's done with plastics as well for very, very fine structures. But I think of it as a close example. It's between powder metallurgy and our thermal spray, because you come and build it one by one, and you will be building up residual stresses is probably what is more important to remember. That's all we have. I'm happy to talk to anybody. You get free advice now that you've taken this class if you want to build something. Yeah.